I just started the recording now.
Perfect. So hello everybody. Thank you for coming to this year's Geometry and Tacos conference. Today's speaker is Richard Wentworth. It's coming from the University of Maryland, and he will start today's first 2-hour session. Will be an introductory lectures. So thank you very much, everybody, for supporting this online conference. You can start anytime. Thank you. If you, if you have any questions, I don't know if with Richard is okay for you to be interrupted during the lectures, or you prefer?
Absolutely, I love to be interrupted.
Okay, great. Otherwise, if somebody cannot ask questions with a mic or whatever, you can write it in the chat, and we will ask, the organizers can ask the questions for you. So yeah, thank you. Sorry, you can start.
Okay, well, thank you very much, and it's really an honor to be asked to give these lectures on a topic, especially where many of my mathematical heroes have sort of made major contributions. So it's also a bit daunting because it's a big subject, as I'm sure many of you know, and it's moved in various directions over the years. So I've got a particular perspective on this, which is maybe not the most up to date, but I'll try to say a few things that maybe are new as well. But mostly, especially in this first lecture, I'd like to give kind of a more of an historical kind of perspective on Hermitian-Yang-Mills connections. Okay, so let me start then with what I perceive as kind of the origins of the subject, which go way back actually. So first of all, an outline. So as I say, I'm going to give some motivation from algebraic geometry, and then motivation from gauge theory or Yang-Mills theory, and those two sort of came together in the late 70s and in the formulation of a conjecture that later became the theorem known as the Donaldson-Becquerel theorem. So my goal here is to sort of, again, give some history and motivation, and then state this theorem. And then, of course, theorems are only useful if they can be used for other things. And so I'd like to give at least one application. And the one that I've chosen here is the Bogomolov-Gieseker inequality. And then in the second lecture, maybe I'll give some ideas of that go into the proof of the Donaldson-Becquerel theorem. I'm not going to try to sort of outline the entire proof, but I think it's more useful rather to give some ideas. Okay, so as I say, let me start from what I perceive to be kind of the beginning of the subject. So let's just take a complex manifold and a holomorphic vector bundle on a complex manifold. So then a connection is a holomorphic connection is one that preserves holomorphic sections. So I can think of this as a map from the sheaf of holomorphic sections of E. We'll always denote this by the curly E. I really mean the holomorphic vector bundle, or really the sheaf of holomorphic sections, into the holomorphic tangent bundle, and satisfying a Leibniz rule. So this is just C linear, and it satisfies a Leibniz rule. When I multiply holomorphic sections by holomorphic functions, then it satisfies this kind of Leibniz rule. So this is what we mean by a holomorphic connection. Okay, and the theorem that I want to start with is an old theorem of André Weil's that goes back to 1938. And actually, I've managed to find the article and locate the actual statement of the theorem. So this is how it's stated, even though it's in a language, of course, it's rather foreign to us now. But okay, so suppose that X is a compact Riemann surface. Then the statement is that this holomorphic bundle admits a holomorphic connection if and only if each indecomposable factor of E has degree 0. So I can write E as a direct sum of indecomposable factors. And the statement is that, sorry, my pen is not working here. The statement is that each of these factors has to have degree 0. Okay, so so in particular, if E is indecomposable, then it has a holomorphic connection, if and only if it has degree 0. Okay, and just let me note that, of course, a given bundle might have many non-isomorphic holomorphic connections. So there could be many different holomorphic connections, and I'll give you an example of that in a second. Okay, so here's one very canonical example, again, on a Riemann surface. Here now I'm thinking of X as being a Riemann surface. So here's a very canonical example of a bundle that carries a holomorphic connection. So this one is an extension of two line bundles. Kx is the canonical bundle, or the holomorphic cotangent bundle of the Riemann surface X. And on a closed Riemann surface, we can always find a square root. In fact, there are many square roots, but we can always find at least one. And then there's an extension of these two line bundles that is not split. So in other words, E is not a direct sum. And in fact, there's only one up to isomorphism in this case. It's not really important that you know why, but let's just take that for granted. And then this one has a holomorphic connection that comes from the uniformization theorem, actually. So we know that X can be written as can be written as a quotient of the hyperbolic the Poincare disk by a Fuchsian group by a discrete faithful representation in L2R. And when we look at that developing map, that's from the universal cover of X onto the Poincare disk, that gives us some monodromy, and that monodromy is the monodromy of a flat connection, and it turns out that that's a holomorphic connection on E. Okay, and it turns out that all other holomorphic connections on E are obtained in this way. So I start with this basic one, and then I can add to that a quadratic differential. So quadratic differential is the holomorphic section of the square of the canonical bundle. And the way that this works, so how do I think of Q? So Q is an endomorphism of E, and the way it works is I first project down to here, and then I use the quadratic differential to come back to the subbundle and then take the injection. And you see that that's the right type because it should be a one form with values in the endomorphism of E. And so I need a one form part. And so the endomorphism from here to here is already a section of Kx. And since this is supposed to be a one form with values in the endomorphism, it's a section of Kx squared. So this gives you all of the holomorphic connections on this particular bundle. And these are called complex projective structures, or in higher rank, this is one particular case of what is now known as an OPER. Okay, so and then just a side remark is that this theorem of A can be generalized to higher dimensions. And in fact, this was one of Atiyah's first papers where he does this. Okay, so that's holomorphic connections. So as I said or indicated in this very construction of this one particular example, a holomorphic connection is already flat. So we're in the case of a Riemann surface. Sorry, we're in the case of a Riemann surface, and so a holomorphic connection on a rank R vector bundle is automatically flat, and so that means that it has some monodromy. So this is the holonomy representation, monodromy holonomy. This is the representation of this flat connection. And so that means that this holomorphic bundle then can be written as a quotient on the universal cover of a trivial bundle. And the quotient is gamma here is the fundamental group. It acts like it does on the universal cover, and then it acts through this representation on the CR factor. And so that means that our holomorphic bundle is actually the quotient of a trivial bundle from the universal connection, from the universal cover. Okay, so a natural question, and this is kind of my motivation, the reason I'm introducing this old theorem, is then you can ask the question, well, can we reduce this holonomy to a subgroup? And in particular, can we reduce it to, say, the unitary group sitting inside of the general linear group? another way to phrase that is we've got our holomorphic connection. Can we find a Hermitian structure on this vector bundle that is preserved under this holomorphic connection? So if the metric is preserved, that automatically means that the holonomy lies in the unitary group. Okay, so that's the question that was asked many years ago, and it turns out that this is not always possible. Okay, so let's take our example that we just looked at, and here I'm going to tensor by the negative square root of the canonical bundle. So this becomes just the trivial bundle then. I've just tensored the exact sequence we had before by this line bundle. And so now I've got a map this way, which is the same thing as saying I've got a holomorphic section, which I'm calling sigma, of this vector bundle. Okay, so let's fix an area form just to be concrete. Let's fix an area form on the Riemann surface X, and throughout I'm going to normalize my constants by declaring the volume of my Kähler forms to be 2 pi. It's just to normalize constants here. And so recall that a line bundle, a holomorphic line bundle, always admits a constant curvature metric. So that's one where the curvature is just the degree of the line bundle times this area form. And here, because of this normalization, I think I've got it right here that this corresponds to the degree of the line bundle on the Riemann surface. So the degree of the line bundle is just I over 2 pi times the curvature integrated over the manifold, and so that's why this normalization is correct. Okay, and just by ordinary potential theory, we can go through this if you like, but ordinary potential theory, you can always modify a given metric so that it has constant curvature on a line bundle. Okay, so now coming back to this example, so suppose that I did have a flat Hermitian structure on this vector bundle E. Then on the tensor product, the bundle that I'm calling V now, then I could take the product metric, and now its curvature would be something like this, right? Because the degree of this particular line bundle is minus G minus 1. So that's where that's coming from. Okay, and it would just be, the curvature would just be central. It's just the identity as an endomorphism of E times this volume form. Okay, so that would be the curvature of this bundle if I had a flat connection, if I had a metric that was preserved by it. Okay, but now on the other hand, V has this bundle that I'm calling V has a holomorphic section. Okay, so now because of the metric structure, we can write down a Weizenbach formula. So here I've written the Weizenbach formula. I think I've gotten it right, but how does this go? So I take the norm squared of the section with respect to this product metric, and I take its Laplacian. And now the Laplacian you can write on the Riemann surface, you can write it as dd bar. And now the whole point of the Hermitian structure and the compatible connections with the Hermitian structure is that you can bring the dd bars inside as covariant derivatives. Okay, and I've done it in this way. And one term that you get when you apply this twice is just the norm squared of the derivative of this holomorphic section, the covariant derivative of this section, and then you get a compensating term, which is the curvature. And if you're careful about the signs here, which I think I've been, then we get an inequality like this. Okay, and okay, so now let's just suppose, for example, that we're in the case of genus at least 2, then you see that you get a contradiction, because if I integrate this over my closed Riemann surface, on the one hand, this becomes 0, and on the other hand, it should be a positive number, so that forces sigma to be 0, which it's not. Sigma is not the 0 section, because as we said, this was injective here, so that's a contradiction. Okay, so this simple example shows you that this one holomorphic connection coming from the uniformization does not preserve a metric structure. Okay, and just as a sort of forewarning here, so I did use something. I used the fact that the integral of the Laplacian was 0 here. So when it comes time, when later on, when we talk about maybe singular connections, then we have to justify this integration by parts step. Okay, so so now so now the question is when does a holomorphic bundle admit a connection, or maybe a flat connection that preserves a unitary structure? It turns out that this is the origin of stability. So simultaneous with this development, Mumford was developing geometric invariant theory, and so he made the following definition in 1963. So a bundle, and this is the key definition for us. So again, let me just do this on a Riemann surface. So, and this is where his definition applied. So if I have a holomorphic bundle on a Riemann surface, we'll say that E is stable if for all holomorphic subbundles that are proper in the sense that they've got their rank in between 0 and E, then this quotient, which is now called the slope, satisfies the following inequality. And so that's what we mean by a stable bundle. And semi-stability is just the case where we allow for equality. Okay, so this ratio, as I say, this ratio here or here is called the slope of E. Okay, so this is a purely topological quantity, so it doesn't depend on the holomorphic structure of E. The degree is just depends on the underlying complex vector bundle. But this condition of stability, of course, does use the holomorphic structure because we're only looking at subbundles that are holomorphic. Okay, so this is the beautiful idea, is that it's a topological quantity, but somehow it's still only applied to those things that reflect the holomorphic structure. And then there's another definition that will be useful for us, and that's polystable. We say that E is polystable if it's a direct sum of stable bundles that all have the same slope. Okay, so in other words, it is semi-stable, but not stable necessarily. So polystable normally means not stable, and so that requires all of the stable factors then to have the same slope. Okay, it's very quiet out there, so feel free to ask questions. Please stop me if I'm going too fast or too slow. Okay, so then let's prove an easy direction of the theorem that I'm about to state. So suppose that E admits a flat unitary connection, then it must be polystable. Okay, so this is the condition that was missing in the previous case. I should say what went wrong here. Let me go way back. Sorry about that. What went wrong here? This bundle is not is clearly not in higher genus. It's clearly not stable because it has a holomorphic subbundle. This has degree 0. Since these two degrees cancel, this has degree 0, and the degree of this bundle, as I say, is G minus 1. So in higher genus, that's not stable. And I'm ignoring the torus case where it's semi-stable. Okay, so sorry about this. So let's prove the easy direction. Then if E is polystable, then it must be sorry, if E admits a flat unitary connection, it must be polystable. So so let's take any holomorphic subbundle satisfying this rank condition. Let me call the rank of S little s. Then we get S is included inside of E, and so that means that the top exterior power of S as a holomorphic bundle is included in the top exterior power of E. Okay, but this is a line bundle, which is normally known as the determinant line bundle. And so again, if I tensor by the dual, then I get this situation. And now we're in the situation like we had before. So we have a holomorphic section of this bundle. If E has a flat unitary connection, then so does this exterior power. And we can run the same argument using the Weizenbach formula that we had before. Okay, and so notice that the curvature here in this case now is minus the degree of S. And so so again, if this degree is positive, then that's going to give us a contradiction. Okay, and in the case where the degree is 0, what that says is that the norm of sigma, instead of being 0, all we can conclude is that it's constant. But then that implies that sigma is actually covariantly constant. It's preserved by the connection, and then it's easy to see that that implies that this sequence splits. So in that case, this sequence splits. It has a splitting. So E is a direct sum of S and Q, and now S and Q both have degree 0. This is the degree 0 case, and now by an inductive argument, you can show that these have to be stable. Okay, so this is that, and that gives you that E is polystable. So this is the argument for this case. Okay, so now the theorem then, and notice the date here. The date here is very, very close after Mumford introduced this notion. So this was exactly the right notion that Narasimhan-Seshadri needed. So here's a theorem that's almost 60 years old now, is that, oh, sorry about that. I decided to use X for everything, but here, this should be X. So the theorem is that a holomorphic bundle on a Riemann surface, a compact Riemann surface of degree 0 admits a flat unitary connection if and only if E is polystable. Okay. So here I've been talking about flat bundles just because I wanted to motivate it from the case of holomorphic connections. But of course, we can extend this to bundles that have non-zero degree by allowing this notion of projectively flat. And so here, instead of having curvature 0, this says that the curvature is a multiple of the identity as an endomorphism. Okay, so so now let me move on to higher dimensions. So so what is the higher dimensional version of this story? So this comes a little bit later, quite a bit later if you think about it. So now let's let X omega be a compact Kähler manifold of dimension n. So for a coherent analytic sheaf on E, we're going to define the degree. Now, instead of just integrating the first Chern class, which is the first Chern class of E, instead of just integrating that over X to get the degree, now we have to, that's not a top dimensional form, and that's exactly where we use the Kähler form. Okay, so the Kähler form comes into the n minus first power to define the degree, and this is well defined. This is just a cohomology class, but since we're on a Kähler manifold, so is omega defines a cohomology class. So this is completely well defined, and then as usual, we'll define the slope of this guy to be this quotient when the rank of E is non-zero. Of course, there are coherent analytic sheaves where this is where the rank is 0, but so we'll only define the slope in this case. Okay, so then the definition of Takamoto in 1972, a few years after the Narasimhan-Seshadri theorem, is that for a torsion-free coherent sheaf on X, we'll call this omega stable if and only if, again, the same condition for all coherent subsheaves, where the rank is strictly between S and E. I think I have a mistake here. No, this is fine. So we have this condition. All right, and as usual, semi-stability is where we relax this and allow for inequality. Okay, so this is slope stability, which is the condition that maybe is familiar to many of you. So let me just make a couple remarks here. So it's really essential that we allow for subsheaves that are not necessarily subbundles. And this is true even if E itself, even if the original thing that we're interested in is a holomorphic vector bundle, we still have to allow for subsheaves. So here I just gave you one, I'm wanted to give you one example where that's really, you see that that's really necessary. So, so let's just take P2 and take a finite number of points. Then it turns out that you can always find extensions. This is the ideal sheaf of the points. You can always find extensions of this form. So here, an extension, in other words, of the ideal sheaf by the trivial line bundle, non-trivial extensions, and in fact, where E is locally free. So E is actually a holomorphic vector bundle. And so therefore, this is definitely non-split extension. So this is something called a Serre correspondence. And so I claim that this guy cannot be written as an extension of line bundles. So in other words, if I had a holomorphic line subbundle of E, then I would have an extension of this type. But now we just compute Chern classes. So if we compute the second Chern class of E, E actually has a second Chern class coming from these points. And the total number of points with multiplicity is basically C2 of E. But on the other hand, if you could write E as an extension like this, you would get that it was minus the square. And since we're on P2, the square is always positive. So this would be a contradiction, positive numbers and negative numbers. So in fact, E doesn't have any line subbundles, holomorphic line subbundles, but it does have a holomorphic line subsheaf. And so in other words, if we only restricted to subbundles, then E would be stable because there aren't any. But here we see that E is not stable. It's strictly semi-stable because we have something at degree 0. E has degree 0 here, and we have something at degree 0. So this is an example that shows you it's really necessary to consider subsheaves. Even if the subsheaf itself is a vector bundle, it may not be a vector subbundle. Okay, one important technical fact that about bundles is that we can restrict ourselves to what are called saturated subsheaves. So those are ones where the quotient is torsion free, and there's always a way of thickening a given coherent subsheaf so that you obtain a bigger one where this property is satisfied. And so here's what I'm saying. So I can always find, so just dividing the quotient by its torsion gives me a bigger subobject with torsion-free quotient. So in other words, a saturated guy. And then the quotient of the original one by this guy is a torsion sheaf. But it turns out that the degree of a torsion sheaf is always positive, is always non-negative, I should say. It's just related to the codimension 1 pieces of the support of the torsion sheaf. And so that means that the degree of this guy is strictly bigger. And it has the same rank. So that means that the slope of the saturated guy is always at least the slope of S. So if I'm only interested in looking at the condition of semi-stability, then that means I can test by saturated subsheaves, and that's good enough, okay? Because that dominates everything else. All right. So, and here's a little fact that's related to the last example. So if E is reflexive, in particular, if E is a vector bundle and the subsheaf is saturated, then S is also reflexive. So on a two-dimensional, on an algebraic, on a Kähler surface, a reflexive sheaf is locally free. It's a vector bundle. And so that means that S is a vector bundle, but just like in the example we just saw, it doesn't necessarily mean that S is a vector subbundle. Okay, so we still have to consider those. Okay, and just a couple more remarks. So unlike in the dimension 1 case, the stability condition now depends on the choice of the class of the Kähler form. So let me go back here. Right here, you see that the Kähler form appears. In dimension 1, it doesn't appear, and in higher dimensions, it appears. In dimension 2, it's linear in omega, and in higher dimensions, it's nonlinear. That's probably going to come up in Karl Tipler's talk tomorrow. He'll say some things about that. another thing I just wanted to point out is that in higher dimensions, holomorphic connections are no longer necessarily flat. And so this analogy that I was making, this motivation rather for the Narasimhan-Seshadri theorem in the Riemann surface case no longer applies, and we have to find a different condition, a different metric condition to reflect this new notion of stability of Takamoto. Okay, so that's the end of my motivation from algebraic geometry, and so now let me move on to gauge theory. Okay, so gauge theory is mostly about Yang-Mills connections. So let me just shift gears here. So here, I guess I just wanted to emphasize that this makes sense on an arbitrary Riemannian manifold. So I have a Hermitian vector bundle on M and a unitary connection, so one that preserves the metric with curvature F. And we call this a Yang-Mills connection if it satisfies this beautiful equation. Okay, so formally, Yang-Mills connections, these are the Euler-Lagrange equations for the Yang-Mills functional, which is just the L2 norm of the curvature. And by the Bianchi identity, we always have that the covariant derivative of the curvature, the exterior derivative of the curvature with respect to the connection, always vanishes. And so this equation, along with the Yang-Mills condition, makes it look like the curvature is harmonic. And so in the case of a line bundle, that's strictly true. So in the case of a line bundle, the curvature is just a two form. And so this is just saying that the Yang-Mills condition is saying that that's a harmonic two form. Okay, so and then one thing that's important, it'll be in the background of everything I say here, is that this thing is gauge invariant. So if I do gauge transformations on the connection, if I look at a gauge equivalent connection, then the Yang-Mills energy does not change. And as a consequence of that, the equations are also gauge invariant. So the set of Yang-Mills connections is preserved by the action of the gauge group. Okay, so so now we want to look at special examples of solutions to the Yang-Mills equations. And so here's a class of examples. So suppose I just take a smooth, so I'm assuming my Riemannian manifold has real dimension M. I take an M-4 form, and I'll say that A is anti-self-dual with respect to this form if it satisfies this condition. Okay, so notice that this works. So if I take star, F is a 2 form. If I take star, I get an M-2 form. Omega is M-4 form, which with F is another M-2 form. And so it makes sense to write down this equation at least. Okay, and in the condition where omega is closed, then this is automatically Yang-Mills. Again, because if I take dA of this side, then I get dA of F, which is automatically 0, and I get just d of omega, which, if omega is closed, is also 0. And so that means that anti-self-dual automatically implies Yang-Mills in the case where omega is closed. But I should point out that these equations are still interesting, even if omega is not closed. And later on, if I have time, there'll be examples of such things. But for right now, let's take this condition as the natural one to get Yang-Mills connections. Okay, and the most classical example is in the case where the dimension of the manifold is 4, and in that case you can just take omega to be 1, which is clearly closed, and these are the classical instantons. So, and they are actually absolute minimizers of the Yang-Mills energy. Okay, so now let's do some computations. Let's take the case where X is our Hermitian manifold, and suppose it has, so here I'm not assuming Kähler, so I'm not going to assume that omega is closed. So, so then we can construct a natural M-4 form by this. So the real dimension is 2n. So this is an m-4 form on X. And so then the condition of the ASD, and this is a computation that I won't do, but it's a nice exercise. This condition for Hermitian holomorphic bundle, let's say with trivial determinants. So here I'm going to remove this condition. This is the analog of this thing that I was talking about earlier. But in this case, the curvature of a connection is the Chern connection for this holomorphic structure is anti-self-dual with respect to this form omega, if and only if it satisfies this condition with respect to the Kähler form. Okay. And so now that leads us to the definition finally of Hermitian-Yang-Mills connection. So let's say that we're on a Kähler manifold, then a unitary connection on this Hermitian vector bundle is called Hermitian-Yang-Mills if it satisfies these two conditions. So if the connection is integrable, so it defines a holomorphic structure on the vector bundle that says that the 0,2 part and therefore the 2,0 part of the curvature is 0, and it satisfies this anti-self-duality condition. Okay, so these are Hermitian-Yang-Mills connections. And here, as I say, I'm restricting right now to the special unitary connections. We're going to generalize this in a second. Okay, so there's a sort of a dual picture here, and that's so here I was talking about unitary connections on a complex vector bundle. Sort of parallel to that is where I start with a holomorphic vector bundle and I ask for a metric that satisfies this condition. So it's a holomorphic vector bundle, so the Chern connection automatically satisfies that, and now I just throw in this extra condition. And you see that these two are sort of parallel. These are called Hermitian-Einstein metrics on the holomorphic vector bundle, whereas the Chern connection of such an object is called Hermitian-Yang-Mills connection. So it's a little bit of terminology that's you've heard probably, but sometimes people use them interchangeably, and this is why. Okay, so as I say, we can extend this to and we want to extend this to non-degree 0 bundles where the determinant is not trivial. I should have said that rather, where the determinant is not trivial, by simply replacing this by the trace-free part. So instead of requiring the full curvature wedge omega to be 0, I just replace this by the trace-free part. So let me again write down some equations now. So again, the determinant of E is a line bundle, and just like we did in the Riemann surface case in higher dimensions, we can also fix a constant curvature metric on this. So in this case, instead of the curvature, the induced curvature on the determinant bundle is exactly this one. And so this is exactly the equation that I was writing down. Now we have to normalize this by n to make the degree work out the way I've defined it. So I'll assume that this is fixed. Okay. And so now when I look at the condition that I just claimed, that the orthogonal part, the trace-free part, wedge omega n minus 1 is 0. That's the Hermitian-Yang-Mills condition, the more general one. Then I can just rewrite that in terms of the full curvature by putting back the trace part. And assuming this constant condition, then I get exactly this. Okay. So this is just some computations that are pretty easy to do. So I'm leaving some of that for you. And now there's another important equality, which is that when I wedge with forms, that's the same thing as contracting with the curvature. So I'm going to write down what this is in a second, but this is the Lefschetz operator, which contracts the curvature with the Kähler form. And so it says that if I take the curvature, if I take any 1,1 form and wedge it with omega to the n minus 1, then that's essentially this contraction times the volume form up to some constant, which I'm being careful about. And so finally, this condition that we had before for the more general Hermitian-Yang-Mills condition becomes this condition. And this is now what we normally think of as Hermitian-Einstein equations. Okay, so and I've normalized things so that this really is the slope of E as I defined it before. So this is a Hermitian endomorphism because the curvature is skew Hermitian. I multiply by I. This is a Hermitian endomorphism. I've contracted, so the two-form part is not there. And so the Hermitian-Einstein equation is saying that this is just a constant multiple of the identity. Okay, so let's see what these look like a little bit more in down-to-earth terms. So let's take a local holomorphic frame for the bundle and holomorphic coordinates on the manifold. And so I'll write the Kähler metric as G, and the coordinates are labeled by indices A and B, and the Hermitian metric with respect to this holomorphic frame by Hij bar. And then this tensor, which we'll give a name to in a second, is just this. So this is what I said. So the curvature with respect to the metric is exactly this. It's d bar of H inverse dH. So in the case of a line bundle, this is d bar d rather of log of H. So in the non-abelian case, we have to be careful. This is the inverse, right? This is the inverse metric. And then we're contracting with the Kähler form. And so this is the left-hand side of the equation in local coordinates. And then the right-hand side is just the identity as I've written it. Okay, so you see what these equations look like then, just formally speaking. If we wanted to solve these equations, if we wanted to solve for H in this case, you see that this is a second order equation in H. And the highest order term is when this H comes outside, and that just gives me the Laplace operator on H then. So this is a quasi-linear term. So it starts out with the Laplace operator on H, and then it's got first order. It's got nonlinear terms appearing in first order involving the derivatives, or quadratic derivatives in the quadratic in the derivatives of the metric. Okay, and as I say, this tensor will come up over and over again, and so it has a name. It's normally called the Hermitian-Einstein tensor. Okay, so again, the easy direction is the following. So we're going to ask for the existence of Hermitian-Einstein metrics and relate them to stability. And so this is a theorem, I believe, due to Kobayashi. I'm trying to get my dates correct here. So Kobayashi and Lübke in the early 80s, is that if E admits, if a holomorphic vector bundle, I should emphasize here, E is a holomorphic vector bundle now. If it admits a Hermitian-Einstein metric, then it's polystable. And the proof is basically the same as the proof I gave before. There's everything goes through to prove semi-stability in the same way. There's a slight subtlety when it comes to the case of polystability. And maybe in the interest of time, maybe I'll just skip this. It's not super important, but it's important that we require reflexivity, or the fact that the sub-object is saturated. Okay, so finally I can state the main theorem of the whole subject, really, and that's the Donaldson-Becquerel theorem. So, so the statement is the following. So if X is a compact Kähler manifold, and if you have a holomorphic vector bundle that's omega stable, so stable in the Takamoto sense, then E admits a Hermitian-Einstein metric. Okay, so let me just give some history to this. So this was a conjecture that's attributed to Hitchin and Kobayashi. I actually have not seen these references. They're kind of hard to actually track down. but maybe somebody can correct me if I'm not right about them. But this is sometimes known as the Hitchin-Kobayashi correspondence, or the Kobayashi-Hitchin correspondence, and I believe that's because it was originally conjectured to them. So Uhlenbeck and Yau proved this for this statement, as I've made it for compact Kähler manifolds in 1986. And Donaldson also proved this theorem in the case of projective manifolds. So he first did it for surfaces, which was the case he was interested in for Donaldson theory. Right around the time of Uhlenbeck and Yau, there was a lot of interaction here, and then he proved the higher dimensional case in 1987. And his proof makes use of the reason that he needs to assume this projective condition is that he makes use of something called the Mehta-Ramanathan restriction theorem, which, again, if I have time at some point, I'll say something more about later. Okay, so as I say, so in the next lecture, I'll give some ideas about some of the things that go into the proof of this theorem, but I wanted to state one kind of application, and that application is the Bogomolov-Gieseker inequality. So again, let's go to a compact Kähler manifold, and this is really only relevant in the higher dimensions. And suppose we have an omega stable vector bundle, then we get this inequality on Chern classes. So R is the rank of the vector bundle, and C1 is the first Chern class, C2 is the second Chern class. So when I square C1, I get a 4 form here that I can integrate against an appropriate power of the Kähler form, and the statement is that that's non-negative. Okay, so in particular, when n is a surface, I can think of these as just numbers. C2 is just a number, and C1 squared is a number, and it gives me an inequality on these numbers. And this inequality turns out to be quite important, actually. It's somehow responsible for the fact that the moduli space of all stable vector bundles is bounded. It can, in fact, admits a compactification. Basically, that's due to the fact that C2 has a uniform bound from below in terms of C1. Okay, so this statement here only has to do with stability, but using the Donaldson-Beck-Yau theorem, you can prove this statement using the equations. And a general philosophy in this whole thing is that whereas this inequality can be sometimes proven just using algebraic means, the case of equality normally benefits from having the actual equations. So in this case, in the case of equality, we can actually say that E admits a projectively flat structure. So that means that the projectivized vector bundle, if you like, has locally constant transition functions. Okay, so as I say, the inequality was proven first for algebraic surfaces by Bogomolov and Gieseker already back in the 70s. And the case of equality was proven by Lübke in 82. So this predates the Donaldson-Beck-Yau theorem. So he didn't know that a stable bundle always had a Hermitian-Einstein metric. So he assumed that he had a bundle with a Hermitian-Einstein metric, and then he gets the case of equality, as I say, because he has the equations. And now in retrospect, we have the Donaldson and Beck-Yau theorem. So this holds for stable bundles generally. Okay, so there's something more I can say about this, but I think I'll stop there because I believe that this is supposed to be about 45, 50 minutes, the first lecture. So maybe I'll stop and we'll take a little break. I don't know, the organizers can tell me what to do here.
Okay, thank you, Richard, for the great talk. Are there any questions?